You try it. Tim Gledhill, who's going to take us on a tour, I think, of one of the most important, dynamically important and early phases in nebular evolution, evolution, when ionization sweeps through and adds an important source of momentum and energy to the entire nebula.
Nope.
Okay, good morning. Mine's this. The motivation for this work, if I can get the slide there. The motivation for this is really to try and understand a little bit more about the transition from the PLN phase, where we expect most of the material around the star to be molecular, to the point where the central star gets hot enough and emitting enough UV to start to photosynthesize that molecular material and photoionize it, which is effectively when the PN turns on. Now, one of the questions I have in mind is how does that shaping that's gone on in the PPN phase of the central star material affect the development of the ionization film, which is going to propagate out through this pre-shaped material. And how it exactly does that is going to affect the appearance of the emergent PN. One of the problems is that there are not many resolved images at the moment of these nascent PN, these objects with hot post-HV stars. So our approach was to use integral field spectroscopy of a small sample of hot post-AGV stars that are IRAS sources. And we're looking at the K-band, so from 2 to 2.5 microns. So this is integral field spectroscopy 2 to 2.5 microns. And in that wave band, we have lots of rovibrational transitions of H2, so we can probe the molecular material. And we also have access to hydrogen and helium recombination lines, like a gamma, for example. So we can look at the ionization as well. And we've been using the near integral field spectrograph NIFs on Gemini North with the alpha AI correction system. So that gives you about, in the recombined images, approximately 0.15 arcsecond spatial resolution with spectral resolution of about 5,000. I'll just say something quickly about integral field spectroscopy in case anybody's not familiar with it. It's quite a well-developed technique now. So you have some sort of mechanism for slicing up a field on the sky. In the case of the NIFs, it uses a mirror system. And these slices are re-imaged onto spectrograph slits. And you use an instrument pipeline and computer software, you recombine all this spectrum to form a three-dimensional data cube. So that's our final product. One exposure is a three-dimensional data cube. So in the X and Y directions here, we've got X and Y on the sky, and then the Z-axis is running through wavelength, so running through the K-band. So that means that for any pixel, say, in our image, we can extract a spectrum, the K-band spectrum, or we can put an aperture over a region of interest and integrate the spectrum for that aperture. Or equally, we can scan through and form images at any point in the cube, so an image of a line, for example, or an image of a continuum at a particular point. So, in a nutshell, that's what we have. We have a sample of about 10 objects. I just have time to run through a few of the results for some of them. IRAS 18062 is quite an interesting object, which appears to have been evolving very quickly over the last few years. It's now a B-type spectral star, but it was A5 in the HD catalogue, and there's evidence to suggest it was still A5 in the 1970s. So its temperature has been increasing very rapidly over the last few years, by at least 200 Kelvin per year. And that's borne out by the increase in the brightly gamma flux. So there's a measurement here in 1999 from Garcia and Anders, and the flux has been increasing pretty much linearly up through our NIFs measurement. And that's what you'd expect in the central temperature has been increasing. And that's borne out by what the gradient flux is doing as well. So the 3-3 continuum, the 8.4 gigahertz flux density, has increased linearly in pretty much the same manner. If you project those trends back, then it looks like photoionization of this object started around 1990, so the PM turned on effectively in 1990, somewhere around about there. Anyway, this is a NIF spectrum in the K-band, so this is the sort of thing we get by extracting the spectrum through the data cube. I've coloured the molecular hydrogen transitions 1 to 0 green, 2 to 1 blue, 3 to 2 red, and anything with another state greater than 4 is sort of browny colour there. And you can see we detect lots and lots of H2 transitions, some of them from high vibrational levels, such as the 8603 line here, as well as the more common ones like the 1 to 0 S1 line, which is the brightest one, and the Q branch down here. So seeing emission from molecular gas here, but also you notice Brachia gamma is very bright, as we expect from this increasing trend here. And we see the helium-1 line at 2.058 microns, and that's indicative of ionized helium in this object. So that transition likely comes from recombination down the triplet ladder and collision excitation across to the singlet state. So that indicates dense gas as well. If we look at the H2 lines, we can form an image, as I said, because we have a data cube. As far as we know, this is the first result imaging of this object. And the 1 to 0 S1 line, you can see that we have an extended structure around the star, roughly about 2 arcseconds across here, with these peaks of H2 emission on either side. And across there is a continuum centroid, and that's roughly the size of the expected photoionization region that's indicated from the radar observations. If we look at high vibrational states, then the fainter material tends to show up. And it has the implication that it's a bipolar outflow orthogonal to this central torus-like looking structure in the H2 there. This is a very similar structure to another object, 19306 -1709, which also shows a toroidal structure in H2. The Brachia gamma and helium-1 emission is not resolved in this object, as you'd expect. The radio modelling suggests that the ionized region is currently radius of less than 0.1 arcseconds, although expanding at about 120 kilometers per second. If we look at, this is an image of the 8603 line. I thought I'd put that in because I've never seen an image of an 8603 line before. You can see it has the same sort of structure as the low vibrational lines. And it shows that we must have UV fluorescence occurring in this torus. And the continuum, well, it doesn't show very much at all. And that's a feature of many of these objects. You don't see any of the structure as scattered light, which you'd expect to do, say, in PPN objects, where you can image them in dust scattered light. And that's a bit strange for this object, because the effective temperature of the log G puts it quite close to a high core mass post-HEB train. So that presumably means that it had a high progenitor mass, and it's evolved very quickly through the post-HEB. So you might expect quite a lot of dusty material in a certain stellar environment, but it's not there. This looks like a slightly hotter object, 24,000 K, around 22025. I'm showing two spectra here, one with an aperture centered on the star and one with an aperture centered on the nebula. And the nebula shows many, many H2 lines, some very faint lines that you don't usually see in photon association regions. We also see Brachia gamma and helium-1. And on the central, we've got the aperture on the central star, the Brachia gamma and helium-1 is very strong. And we see this doublet feature here, which had been identified previously and possibly attributed to magnesium-2. That seems quite a secure identification now. This doublet is likely to be excited by a line overlap, bone fluorescence with Lyman beta, and you expect to see it in H2 regions. It's seen in more evolved PN, and it's also seen in around high mass YSOs, for example, like H-alpha-101. So that's indicating that we have photoionization going on there as well. And we also see quite a nice fun series of this object. So if we look at the H2 imaging, we see quite a detailed structure of this object. It seems to have these arcs of emission coming out from the centre with knots and bow shock-like features at the ends. That's the 1-0S1 line. We can also image the Brachii gamma in this object. That's deconvolved with a standard. So that's an image of the Brachii gamma line, and it's showing this ring-like structure with these extensions on either side. And combining that with the H2, you can see it fits inside of this H2 structure. And we also imaged one of the Mg2 line doublets, and it has a very similar structure to the Brachii gamma, which again confirms that it's probably due to line and breach when it's tracing the photoelectric emission. And finally, again, not much in the continuum again, considering we've got all this emission out here, there's diffuse H2 further out that I haven't said very much about. If we deconvolve the image, there is some structure which does sort of tie up with the H2, but it's hard to really spot the structure around these objects in the continuum. 19336 is probably a more evolved object than those two. It's the only target in our sample where we don't see any structure in molecular hydrogen at all. The H2 line seems to be constant across our 3x3 arcs in this field. But we see very strong Brachii gamma here and helium-1, and again this magnesium-2 doublet and the flat series, so we've got ionized emission here. We can image the Brachii gamma, and if we do that, we see quite a nice nebula around the object. So a bipolar lobe, so a northern and southern lobe, there's this sort of equatorial enhancement of emission on either side, and that structure agrees with the radio imaging as well. The radio imaging indicates you've got density enhancements on either side here, because the emission of that frequency is optically thin. So there's a lot going on here. There's possibly a third lobe, so this could be multipolar. There seems to be an axis going this way as well. We've managed to deconvolve the helium-1 line in this object as well. And the helium-1 line, 2.058 microns, has this sort of ring-like structure that sits right inside the Brachii gamma emission. This is a continuum image, so in this case you can see elongations of the continuum image, but all of these objects are very dominated by the bright central star. So that shows the advantage of using this intracritical field technique. It's basically a contrast enhancement technique, because everything's recorded in the same cube, you get a very good continuous attraction you can take off this bright central star. And the last object I'm going to show you, just to show you that they're not all incredibly bipolar. This is 19200, it's a study called 57, a B-type central star. It's the only one of the ones I've shown you that seems to be carbon rich. It's got PAH features and also a 30 micron feature in its SED. This is an image in molecular hydrogen, 1-0S1 transition, and it shows this nice round ring, although there's emission in the centre as well. So this is probably a limb-Brighton shell that we're looking at. Spectrum, as well as the H2 lines, we have the usual Brachii gamma, but there's no helium-1 emission here, so it doesn't look like we started to ionize helium-1 here. And the atomic lines are unresolved in this object, so again, this is probably an earlier stage, but the photoionization region is still unresolved. So I'd like to finish rather than with some conclusions, with some questions, really. One of which is these objects don't seem to be very dusty, so where has the dust gone? We can't detect these objects really in scattered light. They're dominated by the bright central star. And that's strange in the case of 18062. It is a high mass object. It's evolved very quickly from the AGB. It must have been mass along the AGB. So it's rather unusual that we don't have lots of material in the environment. And what sort of objects did these targets evolve from? What do they look like in the PPM phase? What were their antecedents, basically? Did they evolve from optically thin PPM? They must have probably been bipolar, because we see the structures, often bipolar structures in molecular hydrogen. But none of the stars are obscured at this stage by dense disks or tori, they're very visible. And in the PPN stage, did they have H2? They probably didn't, because H2 in the PPN stage relies on fast collimated outflows from shocks. So perhaps these objects evolved from optically thin PN, which means optically thick PN probably evolved into something else. The ones that have H2 in the PPN phase, the ones that have shock excited fast winds, they evolved into something like AFGL 618, for example, which will be its own central star, but lots of obscuration. So some questions rather than answers.
And Joel.
So I'm a little bit concerned about your worry, or your concern that you are not seeing that kind of light. I mean, isn't the simple explanation that we have a very high central source? It's very hard to see the scattered light because scattered light is very hard to faint. Scattered light because of infrared comes out fast.
Yeah, I mean, the stars are very bright, but we've got pretty good AO correction in the system. So
it's a quantitative question. Can you rule out the presence of faint scattered?
Sorry?
It's a really a quantitative question.
Qualitative?
Quantitative question. That the fact that you're not seeing scattered light doesn't just that you're not sensitive to the amount of scattered light that you might expect, but you can't see the rest of the ESF evolution.
Well, I think it indicates there's not very much dust out there because the central sources aren't that obscured. I mean, if you look at the extinctions, they're not very high, even in the optical. In some of the cases, we can detect scattered lights. And we know there is dust around these stars because it's visible in the infrared, in the SCD, okay, this is these objects. So perhaps that emission is coming from quite close to the star. Indeed, it probably is because of warm dust. So in some of the cases, we've tried quite hard to deconvolve the continuum just to detect that perhaps a dusty torus close to the central star within 0.1 arcseconds or so. But it's pretty hard to do that. But there certainly doesn't seem to be any dense, dusty, extended structures that link up with molecular hydrogen emission.
So time for one short question, Joel.
Actually, I think you just answered my question in answering my
That's a
question.
good short.
I just wanted to add a comment. Those are the most beautiful IFU images I've seen to date of this sort of object. And so clearly this is the way to go in the future.
Yeah, this is a fantastic instrument, especially considering its start. I really didn't make it.
So, welcome to our next speaker, Martin Riviera. Asymmetric expansion of 40 planetary nebulae.